Hello, everyone. Welcome, and thank you for joining this final session, part of the Toronto Machine Learning Society Summit on day 2. This session is data shift and model adaptation in ML with Sedef Ali and Mehdi. My name is Faraz, and I'm one of the co-organizers here at TMLS. Just before we begin, if you have any questions, please feel free to ask them in the chat. And lastly, just a quick reminder that the talks are going to be hosted on Hopin on the 17th and 18th. You would have received an email yesterday. If you don't have it, please do message me here. So without further ado, I'm going to hand over the virtual mic.
Thank you. Thanks, Faraz. Hello, everyone. It's great to be here with you. So thank you all for participating in our workshop session on dataset shift and model adaptation in machine learning. So my name is Sedef Akinli Kocak, and I'm doing the introduction of this session. So let's kick this off by looking at the agenda of this workshop. We have 3 sessions. In the first session, I'm going to introduce our organizing team and Vector Institute and talk a little bit of what the Institute does for those who don't know. Then I will give you a bit of background of how we responded at Vector, the dataset shift in recent pandemic, and our latest technical report. Second session, we are going to talk about data shift types, detection, and potential remedies in details. Then we'll get your questions. In final session, we are going to introduce advanced topics such as transfer learning and active learning, and followed by hands-on practice. We are going to complete the session with Q&A. Few housekeeping items. Feel free to write your questions on the chat during the sessions. We will try to respond them on the chat. Alternatively, you can wait the Q&A sessions after each session and ask your questions by unmuting yourself. We have hands-on practice session towards the end of the workshop. Here is the Colab link that we are going to use in the practice session. We will put this link on the chat as well. So let me introduce our workshop organizing team. So I'm the Applied AI Project Manager at Vector Institute. My focus is industry applications of machine learning. I'm also a part-time data science and analytics lecturer and supervisor at Ryerson University. Next is Ali. Ali, please introduce yourself.
Hello, everyone. As Sedef mentioned, my name is Ali Pesaranghader, and I am an AI research scientist at LG Toronto AI Lab, and I am very excited for this talk. Mehdi.
Hi, everyone. I'm Mehdi Atori. I'm also a postdoc researcher at Autodesk, and happy to have this session for you. Thanks for joining.
All right, so let me talk a little bit of Vector Institute. You may all know the Institute is a non-for-profit research institute with its mission to lead Ontario's effort to build and sustain AI-based innovation, growth, and productivity in Canada by focusing on the transformative potential of machine learning, specifically deep learning. We work together with our AI partners in other parts of Canada, with Canadian industry and public institutions to ensure that they have the people, they have skills and resources at the use of AI. So some numbers that may help you to understand Vector's AI community. These numbers from our latest annual report. We have 617 researchers, including faculty members, affiliates, postgraduate, graduate researchers, postdoctoral fellows, and undergraduates. So far, over 4,000 participants joined Vector's industry programs and developed their proficiency required to execute AI projects. Vector has more than 45 industry sponsors and provide programs, courses, and collaborative projects to help businesses. And more than 1,400 master students began their studies this year in the combination of Vector recognized programs and individual AI study paths in Ontario. So Vector is more than a research institute. So Vector's industry innovation team, where I work, this team leads industry collaborations with applied AI projects. Our projects bring industry and researchers together to apply state-of-the-art solutions to specific industry-related problems. Last year, we established Dataset Shift project with our industry sponsors and researchers with a goal of deeper understand of dataset shift, its varieties, effective detection strategies, and adoption techniques. This project reflected the reality companies faced as business conditions and dataset evolves. We worked with 3 different datasets: cross-sectional, time series, and image. And we recently released the project technical report, including our work, results, and insights. In the cross-sectional data, the aim was to detect covariate shift and to adapt algorithms and techniques to account for it. In the time series data, the aim was to use transfer learning and adaptive learning as a means to tackle dataset shift in retail industry specifically. And the image dataset, the aim was to use few-shot learning method using very limited training examples to classify new dataset. If you're interested in learning more about our project and read techniques and work, please visit Vector's website, and the report link is given in the slide, and we will post it on the chat. So this project was inspired by the recent COVID-19 pandemic, which has caused behavioral and economic pattern shifts so drastically that there is limited data indicative of current economic and social conditions. So what is a dataset shift? We all know machine learning systems are trained under the assumption that training data and real-world data will have a similar distribution patterns. Let's look at this example. Let's imagine a model using historical data from last 10 years to predict jobless claims in the US. In practice, the model correctly predicts around 200,000 claims for the 4th week of March 2020. Then the COVID-19 hits and unemployment claims skyrocket. Our model predicts around 800,000 claims. It's higher than a normal, but is this reliable? In reality, these claims are over 6 million. Another example, to predict the toilet paper sales. Do you trust the reliability of your model prediction? Probably not. In the dynamic industries and changing circumstances, such as pandemic, new data distribution patterns can be different, significantly different from the historical pattern used for training. Therefore, they have a major impact on the reliability of the predictions. So this difference between training and the test data is known as a dataset shift, and when severe enough, it requires adoption. As we've seen in this example, during the pandemic, the model parameters have dramatically changed, such as layoffs or closures, mobility, etc. This model trained on historical jobless claim data may underestimate the effect of the pandemic. So at the beginning of the pandemic, companies were trying to use their data and algorithms optimized for, let's say, toilet paper, right? Because we are lack of them. And then end of the spring, people were buying bicycles to go out and get more fresh air. At the end of the summer, people were buying gym equipments because the gyms were closed. As consumers around the world adjust this next normal, that there is a significant variance in consumer sentiment and behavior across countries. In most countries, consumers intend to continue shifting their spending to essentials while cutting back on most discretionary categories. Now businesses face with new customer personas, and they're going to have a transformative impact on the future businesses. So we have to encounter those new personas. Not only supply chain affected by behavior change, but also affected by AI, causing hiccups for the algorithms that run behind the scene in inventory management, fraud detection, marketing, and many more. So machine learning models trained on normal human behavior are now finding that normal has changed, and some are no longer working as they should, right? So machine learning models are designed to respond to changes, but most are also fragile. So they perform differently when input data differs from too much from the data that they trained on. So it is a mistake to assume that you can set up an AI system and walk away. So you have to be aware that AI is a living engine. So, so we see that the pandemic has a severe impact on the dataset shift, but the data shift is an ongoing challenge in several industries and services where distributional shift is everywhere. So for example, like climate change models, like financial shifts, shift in retail and sales. So modern translation systems, for example, like Google Translate, often encountered atypical and unusual use of language in their translation queries. This typical includes like slangs, poor grammar, orthography, and like punctuation, as well as, let's say, emojis, right? So this poses a challenge to modern translation systems, which are typically trained on corpora with more a standard use of language. Therefore, it's important to models to be robust to a typical language use and provide high quality translations under such a shift, as well as indicate when they're unable to provide a quality translation. Here are some of the potential consequences of not handling the dataset shift. It could be a loss of lives, loss of customers, resources, time, trust, and reputation. For example, like data shifts are frequent in biomedical research because of recruitment biases. When the dataset shift occurs, standard machine learning techniques do not suffice to extract and validate biomarkers. But biomarkers, as you may know, are important for diagnosis, prognosis, and treatment or risk assessment. So predictive biomarkers extracted through datasets, which has dataset shift, are not safely used in clinical practice. So this may lead to wrong diagnostic and treatments. So here are more detailed consequences of not handling dataset shift. I'm not going to go into the details of this list, but the key takeaway is always check your dataset, investigate, and mitigate. So now I'm handing over to Ali. He's going to start with terminology, then move on to the adaptive learning, how to detect shift and data shift types. Over to you, Ali.
Okay, thank you, Sedef. Would it be possible to answer any question that audiences may put in the box? Yeah, thank you. Let me share my screen. And, okay, let's start. Thanks everyone again for your interest in this talk. This is the outline of my presentation. I start with some terminologies like adaptive machine learning, data shift, and then talk about possible approaches for responding to data shift. And then I talk about different types of data shift, which are covariance shift, label shift, and concept shift. Oh, there is a typo there. And the objective of this presentation is knowing about adaptive machine learning, what I know about data shift types and how we can address and adapt our models in order to react to data shift. And then I also talk about evaluation metrics and how we can assess our shift detection methods. I will also share public frameworks and resources, and then share a rule of thumb for dealing with data shift. So let's start with adaptive machine learning. We know that the traditional definition for machine learning is that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. However, in many real applications, our models or the computer needs to adapt systems to a changing environment. And this is the definition for adaptive machine learning. So in that case, a computer system learns if it improves its performance or knowledge due to experience, or if it adapts to a changing environment. And like traditional machine learning, we have adaptive supervised learning, adaptive unsupervised learning, and adaptive reinforcement learning. And during this workshop or tutorial, our focus is on adaptive supervised learning. So let's talk about what data shift is. traditionally, models are trained under the premise that the training and the deployment data are from the same distribution. However, in real world, it may not be the case, and the distribution between the distribution of our training data and the deployment data may differ. And this phenomenon is known as data shift in machine learning community. And in order to respond to data shift, there are two main approaches. They're called reactive data shift detection and proactive data shift detection. In case of reactive, we react once data shift happens, and we use a statistical adaptation or correction, transfer learning, and adaptive learning. And reactive solutions are easier, but more risky because we react after something happens, right? And if this delay is long, it could be risky, for example, in health domain. However, in proactive case, we react before something happens, and because of this, it is harder because we need to be an oracle, and solutions for having proactive data shift detection is adding mitigation steps in our ML pipelines, or using data or model repositories, and if something is likely to happen, we refer to that repository and extract models which may fitable to the situation. And the other solution would be simulate data shift with respect to different situations. As I said earlier, proactive is harder because we need to be an oracle and foretell what's going to happen before it happens, and because of that, it is less risky compared to reactive case. And now I'm going to talk about data shift patterns and types. We have 4 data shift type patterns, which are abrupt, gradual, incremental, and recurring. In the abrupt case, there is a sudden transition from one distribution to another one. In gradual one, the transition is slow, so it doesn't happen quickly. In case of incremental data shift, we experience a few intermediate distributions between 2 distributions, which are referred to as source and target distribution. And in case of recurring or seasonal data shift, we experience some distributions once in a while. For example, traffic data distribution may change from one season to another, but its distribution is similar for every winter or every spring. And we have 3 main data shift types, which are known as covariate shift, label shift, and concept shift. Covariate shift happens in our features. Label shift happens in our labels or classes, and concept shift happens when our decision boundary changes or we are going to use our data for another task. So before talking about data shift types and how we can address them, I like to talk about these notations because they're used shortly. So S stands for source domain or training domain. T stands for target domain or inference domain or test domain. And PX is the probability distribution of data X, and PY is the probability distribution of our labels, and Px given y and Py given x are our conditional probabilities. And you may know about the bias theorem, and it is often used by research community in order to define data shifts. So let's start with covariance shift and explain how we can detect it and then adapt our models. So as I said earlier, covariance shift happens in our features. That means the conditional probability of y given x remains the same between our source domain and target domain, but Px changes. That means Psx and Ptx are different. And covariance shift happens because of lack of randomness, inadequate sampling or bias sampling, and non-stationary environments. In order to detect covariance shift, there's different solutions, but for this talk, I only cover domain classifier. And if you're interested about this solution, you can refer to this paper. What domain classifier does is that it reduces the data dimension to a single dimension, and then use that single dimension to decide whether an instance is from the source domain or the target domain. And if the error of classifier is great, that means that the distribution between our source and target are close, because that means the domain classifier was not able to distinguish the two distributions. And in order to see what features cause the shift, we can use feature importance analysis. And also this solution is an offline. This solution is offline. And let's say we trained a domain classifier, and we want to see if it was able to detect covariance shift. So we have our test data, and we have our training data, and or our source data or our target data. We train our domain classifier and measure its accuracy score. If the accuracy score is over 0.8 or it's over 80%, we can say the domain classifier was able to detect covariance shift. Otherwise, it failed. For example, in this case, the source and target distributions are similar. That's why the classifier AUC is not that great. Also, we can support this observation by binomial testing. And I passed this slide because of time. And if you had question, maybe I can refer back to this later. Other solutions other than domain classifier are principal component analysis or PCA, sparse random projection, and autoencoders. We use this dimensionality reduction techniques to reduce the dimension of our source and target domain, as you see in this picture. And then we can apply two sample tests and followed by combined test statistics to detect data shift. And as I shared earlier, you can refer to this paper if you like to know about the details of how we can use PCA or autoencoders in this architecture. So far we talked about covariate shift and covariate shift detection, and now we want to talk about adaptation. Adaptation means we need to adapt our models in order to reflect data shift. So Sedef, is it possible to answer the question? And so for covariate shift, what we do is one of the solutions is sample reweighting. In this case, we assign weights to instances, and instances which are likely from target domain or they're close to the target domain are going to have greater weights. And we will use these weights in our loss function when we want to adapt our model. So these weights are calculated using this equation, and beta is the ratio of the probability of belonging to source domain over the probability of belonging, the probability of belonging to target domain over the probability of belonging to source domain. And this Sudoku explains the details. For example, this one, this set is our training data, and this set is our test data. As you see, it is unlabeled. In order to train a domain classifier, we create this set. So we extract x1, x2 to xn from our training data, and we assign label 1 to these data points, and then we extract u1, u2 to um from our test data or our unlabeled data, and we assign label -1 to this data point. So as you see, we have this set of data, and then we train a binary classifier over these examples. And then we calculate beta using this equation, the probability of belonging to target data over source data. And then once we calculated betas for every instances, we keep those, we extract those which are for training data, and then we apply them in this loss function. So we have these weights applied to the loss for every example. And this is an example for showing how sample reweighting help us to adapt to our source data, target data, sorry. So we have these blue data points which represent our source data, and we try to feed a linear model to this data set. And we have these red data points from our target data, and this red line doesn't do a good job for this red data points. So after applying sample reweighting, we get these weights for every instance, and by applying these weights in our loss function and retraining our model, we get this adapted line to the red points. Another example is this one. For example, we try to estimate the sigmoid curve And in our source data, we have this blue data points. And we have a few examples for examples from this tail in our source data. That's why if we train a model on source data, it doesn't do a good estimation on this tail. But if we do sample reweighting, we were able to have a better estimation for both tails. And as you see, we had our estimated function adapted to these red points. So far we had, we talked about covariate shift. Next, I'm going to talk about label shift. So
Ali, before
yes.
you go into the label shift, can you just explain a little bit, elaborate of source and target domain once more?
Yeah, source domain or source distribution is a distribution that we sample our training data from, and target domain is the distribution that we sample our inference or test data from. Yeah, you're right, Mehdi. Oh, okay. Yeah.
Thanks.
Is there any other question or?
No.
Okay. So let's consider label shift. So label shift happens when we have some shift in our labels or classes. So in this case, PX given Y remains the same, but PY changes. So that is PSY and PTY are different. And this kind of shift happens because some concepts are oversampled or undersampled in our target domain or in our test data or deployment data. So how we can detect label shift? Detecting label shift is harder compared to covariate shift because we don't have access to real labels for the target distribution or target data. What we can do is we try to do some estimations here. So we have our own classifier, a pre-trained classifier F. We take out a random holdout set from our source data or training data, and we train our classifier on the remaining part. And we call this classifier label classifier. And then we apply this label classifier against the holdout set and our real target data. So by applying that label classifier against holdout set and target data, we get these two distributions, probability distributions, and then we can compare these two together and see if any shift has happened. So if these two components are different significantly, we can suggest we experience label shift. Otherwise, we need more observations or proofs. In order to conduct the test, we can use black box shift detection approach. We can use a black box shift detection approach. An example of the test that we can use is Kolmogorov, Smirnov, Anderson, Darling, and maximum mean discrepancy. So if you like to know about label classifier and black box shift detection more, please refer to this paper. And And so this one was for label shift detection. And now we can talk about label shift adaptation. So, so in covariance shift, we try to assign weights to instances, and we can apply similar idea here, but instead of instances, we try to find weights to, we want to assign weights to our classes. As I said earlier, label shift may happen because of because some concepts are oversampled or undersampled in our test data. So by finding these class weights, we can adapt our loss function in order to react to label shift. So, so for calculating this, we need to estimate PA-TY because we don't have access to PA-TY, right? As I mentioned before. So in order to estimate that, we can use our confusion metrics, which is confusion metrics of our classifier, which is trained on our source data. And then we calculate this average for every class. So it means how often we label an instance to this class over considering all instances. And by solving this equation, so I don't talk about details in this talk. It is beyond the scope of this talk. But Zachary Lipton explained how they derive this equation. And so we got this estimation from this equation. We apply it to this equation, and we have our classifier confusion matrix, right? And by solving this equation, we can calculate weights or W's. And once we have these W's, we can apply them into our loss function by assigning weights to our classes. And this is the Sudoku for what explained earlier. And yeah, so we talk about label shift. We define what label shift is, and then explain how we can detect label shift and cover how we can adapt our models in order to react to label shift. So now I'm going to talk about concept shift. Concept shift happens when PY given X changes, and that happens when our decision boundary changes or we are facing a new task. Concept shift adaptation could be global or local. In global case, we retrain our model from scratch. In local case or local adaptation, we only adapt some part of our decision regions, and this is only applicable to granular classifiers like decision trees and decision rules. And this is an example of a concept shift. For example, if we had trained a model in context 1, we couldn't use it anymore for context 3. So in that case, we need to adapt our model. And this is just an example for showing concept shift. And it is known as circle data set in literature. And And in order to detect concept shift, we use a statistical or probabilistic methods to bound the difference between these two distributions. And we estimate this to distribution by the classifier performance. And if the distribution, if the difference is significant, it triggers for data shift, or we alarm that data concept shift has happened. When you research for concept shift, you will see that many of these works are done for data stream situations or settings, but they're applicable to offline setting or batch setting as well by making some small changes. So there are three main groups for concept shift detection methods, and there are sequential analysis, statistical-based methods, and window-based method. And in sequential analysis, we evaluate prediction results and allow for concept shift when a predefined threshold is met. For a statistical ones, we analyze parameters such as mean and the variance, the standard deviation associated with the prediction results. And in window-based methods, we have two windows or sometimes one. And we summarize the elements inside the sliding window. And if there is significant difference between the distributions of the elements inside the sliding windows, we allow for they allow for data concept shift. And these are well-known methods for each group in the research community. And among all, I took one example which I introduced in 2016, and it is called FHDDM, and it applies Hafting's inequality or Hafting bound. And what it does, it slides a window on prediction results. P is our prediction result. It is either 0 or 1. If it's if our prediction is correct, we insert 1 into our window. Otherwise, we insert a 0, and we slide the prediction our window over the prediction results over time. And using Hafting's inequality, we calculate this stats. And if the difference between and also these registers, and I explained them now. Mu t is the mean of elements inside the sliding window, and mu m is the maximum mean that we observed so far. And the difference between these two means suggests concept shift. And I covered this earlier. So for concept shift adaptation, there are two solutions. We have blind and informed. In the blind case, we adapt or retrain a model once in a while. In the informed case, we use shift detection methods to detect concept drift or concept shift. So in case of detection, considering the nature of our model, we can go either partial replacement or complete replacement. For example, let's say you have a naive based classifier. In that case, you need to have a complete replacement. Or if you are having some sort of decision tree, you can consider partial replacement. For example, CVFDT and VFDTC are examples of incremental decision trees that are used to that are trained incrementally over time and they're expanded over time, but they're able to adapt themselves to concept shift. And for evaluation metrics, we can rely on correctness measures like accuracy, precision, and recall. For shift detection, we can consider shift detection true positive, false positive, and false negative. And we prefer a shift detector that has the highest true positive and lowest false positive and lowest false negative. The other measure, which is very important, is delay of detection, because in some application, if the delay of, in some application, we need to have a very short delay, detection delay. For example, in health, we don't want a method that would allow for a drip after a while. We can also confirm the performance or assess the performance of our shift detection method by considering the model's accuracy or loss, and see whether applying shift detection methods is beneficial or not. And this is a framework for counting true positive, false positive, and false negatives for shift detection. And it is used in the research community. By the research community, we have this interval. If we allow for a data shift within this interval, we count one for true positive. And if we allow for any data shift which does not exist, we count one for false positive. And if we miss alarming for a true data shift within an interval, we count one for false negative. For resources we have Alibi Detect, Scikit, Multiflow, Tornado. These three frameworks are written in Python. We also have MOA, and it is used by research community since it was one of the earlier works for data shift detection, and it is written in Java. And Scikit Multiflow is Python version of MOA. And Modal is a framework for active learning. Mehdi will talk about it later. And for data sets, you can use synthetic data sets like sin1, sin2, mix, stagger, equals, and LED. If you like to have these data sets, you can refer to my GitHub. I have shared a few examples for every one of these data sets. And for real world data set, you can refer to a MOA's webpage. They have a data set section, and they cover AWS price, electricity, and forest cover type data sets. And for final points, I have these. Always keep track of your data and your model performance. If your model accuracy drops significantly, something is off. Most likely it is due to some shift in your data. And the significant levels vary from one domain to another. And if we can't detect data shift, it doesn't mean data shift doesn't exist. We have to try other methods as well to increase our confidence. And domain knowledge helps a lot for dealing with data shift. And different types of the data shift can co-occur together. For example, we may experience covariate and label shift together. So we need to have all these methods running and check if we are experiencing any data shift. And we can use model repository for recurring concepts. And later on, we can use those models for transfer learning. And finally, we need to keep track of influencers, especially these days. For example, if we had a model to predict Dogecoin price, I doubt it would work in early February, because Elon Musk tweeted about Dogecoin in early February, and the price just went up sharply, right? So in this case, we need to keep track of influencers and make sure that we consider all aspects which impact our decision making. Yeah, that's all I had for today. And next, Mehdi is going to talk about advanced topics like transfer learning and active learning. And I can take 2 questions now, or we can talk about them at the end of the workshop. So this question is kind of application specific. Do you like to explain a little more, Ramin, about what kind of conversational agent you're using and what is the task? I stop sharing now. I can reply to Ramin in the text chat box, but if you can track the user dialogue distribution over time and see if there is a difference. You can allow for data shift, or for example, if you want to track sentiment during the conversation, you can do that by just checking the model's output and performance.
We have a few more minutes. If you'd like to ask questions, please unmute yourself. Maybe turn on your camera, so that will be also great.
So when we calculate weights, it is not just we don't only consider our training data. We also rely on our test data as well, even though it is unlabeled. So in that case, our weights are not fixed. Might there be some way to consider? Maybe we can do, so if you have multiple test data over time, maybe you can average weights, or average weights, or apply like weighted average. You can do some tricks.
Okay, so let's move on to Mehdi.
Yeah.
Okay, thanks everyone for joining. And hi again, I'm Mehdi Atoi. All today I'll talk about a few more, I would say, advanced topics in data shift. And so these are the techniques that are usually used to avoid data shift and use the information that you already have from your trained model and reuse it to come up with a better model. So what's happening in reality is that if we can have this type of perspective for data shift, that you have a model that you have trained and it's not performing as well as before because of data shift. And what I'm going to discuss are the techniques that are usually used to not throw away all the knowledge that your model has learned on your trained data set, and how you can reuse that information or adapt it in a way that it's still applicable to the current to the data that you have in your target data. So that's the goal of the talk here, and I'm going to focus on transfer learning and active learning methods. All right, so first we're going to give you an introduction to transfer learning and talk about transfer learning under different settings. Next, we'll have the same discussion on active learning and introduce a couple of active learning techniques called pool-based and stream-based learning. And we'll talk about the uncertainty sampling techniques that are used in active learning. So since I'm going to use some of the terminologies again, not in a very sophisticated mathy way, just so that everyone is on the same page, I'll just reintroduce some of the notation that we used. We call the source domain with the distribution with PS. So S is just for the source, for the domain, for the source domain. And our feature space is XS YS, and the target domain is distribution is P tau, which I think Ali used a T for it, but it's just they're the same. So tau is for target, and also it has its feature sets. And our goal is to find the hypothesis HD, the model that you're looking for, that maps the feature space of the target to the output that we want. And our goal, and we want to use the knowledge that we gain from the source and that minimizes the loss function, which basically means we want to train a data model on a training data set and use it on a test data set. And we want that model to perform as well as it did on our training on the test data set. That's what it means, just the terminology that we're going to use. And let us donate our tasks as TS, which in this case, we're only talking about labeling tasks. So TS is a set of the labels that we have, and the distribution of the relation of the distribution of the labels with respect to our input parameters, and simply these Y's are labels. So from just call it, we have we have n labels, and Y represents the labels, and PSY given X represent the the relationship between or feature space and the output. Okay, so let's go to the transfer learning. The goal of the transfer learning is to use the knowledge that we have gained by machine learning model and apply it to a different domain or task. That's why I introduced those notations before. We want to talk about these domain and tasks and how they're related to each other. So we have a model that works on one domain for a specific task, and we want to apply to either to change the task or we change the domain. And why we want to do that? Because it allows us to reuse the model. It allows us, if you want to retrain the model, it allows us to have a better higher start. So instead of starting from a random guess, you can start with a higher start, so your model has some knowledge about that domain, and would reduce your training time. Also, the training rate can be improved, not only the training time, but also the training rate. And also, it could be possible that your model at the end of the training would perform better compared to a model that you didn't reuse any of the knowledge for. So the goal is to make your training efficient or reuse your model if that's possible. Sometimes it's not. Sometimes the changing domains are so different that it's very hard to map those data sets together and reuse your model completely, but at least it will give you a better, higher start. So there are two cases that we make sure that that's the only one that looks weird. So this is the H tau, so which the target hypothesis. I'm not sure why it's there. So the goal is to improve the learning of the target hypothesis, which is our model basically. And there are two cases here. One is that your domains are different from each other. S is not equal to tau, or your tasks are different. And we'll go through the examples of what it means for these two things to be different. Okay. The first case is that imagine your feature space are same and your tasks are different. So what does it mean? One example is that imagine you train a model on CIFAR-10, which is a data set of images that have 10 different classes: airplane, automobile, trucks, and ships, but there are only 10 of them. And there's another data set called CIFAR-100, which uses the same type of images as input, but the only difference between these two data sets is that CIFAR-100 has more classes. So the number of classes are different here, but your feature spaces are the same. They're just colored images of some dimension, right? So this is the first case that we have the same feature space, but different tasks. So in this case, when the labels L spaces are different, this is the most conventional and mostly used type of transfer learning. Is that we can reuse the pre-trained model on, let's say, CIFAR-10 to do the classification on CIFAR-100. And the way that we do it is, and the idea is that we can, the earlier layers of a neural network, imagine the model that we have trained is a neural network. The earlier layers of a neural network, they have higher, lower level, they understand lower level representation of our images, let's say edges and corners and stuff like that. So we don't need to kind of retrain the model to detect edges. So we can take those earlier layers in a neural network and only train the later layers, let's say just the last layer or a few last layers of a neural network. So you can basically maintain those weights and only adapt the weights of the final layer or final layers of your image. So, obviously, you have to change your last layer so that it can, instead of 10 classes, it's detecting now 100 class for the example of the CIFAR-10 versus CIFAR-100. And that allows you to reuse the knowledge gained on CIFAR-10, and you can turn off the training on your earlier layers, which means that the number of parameters that you're training decreases significantly, and that helps you in the training. You need less memory, you will train faster and converge faster. So that's the most classic way of transfer learning that many of you have probably used by now. And so this is an example of how earlier layers may learn more about the abstract features, such as edges and corners. And this is from this paper, and you can see the layers, the early layers, actually just trying to detect edges and corners or curves inside your image. But when you go further in your I don't have the images here, but if you go further and further inside your layers, the images more represent your data rather than abstract features. And that's where the idea comes from, that the earlier layers are reusable. And this is an example of that. Imagine that this is a training image. You have you train your model and on this data set to detect tiger cat, different types of cats, I guess, or camping cat, Hatao, I got it from this paper. So there are 3 classes here in this data set. And so we can reuse the weights of these layers, froze them, and only, let's say, fine-tune the last 2 layers of this network for a new task of detecting malignant or benign cancer cells. So and that would reduce the training significantly. And if you actually do that, you figure out that for the same cost, training cost, the performance is significantly improved. Okay. So we have another type of condition that would cause us to have the same domain and different tasks. The first one that we discussed was that, okay, the number of labels, the class labels are different. Okay, that was the first one. But if you remember, these tasks, they also have the relationship between them. So if I go back to the terminologies that we introduced, these tasks are composed of our label sets and also the relationship, basically the relationship between Y and X. And another one way is that the tasks are different, label sets are different, which we just discussed. And the second condition is that the relationship between the inputs and outputs are different. And this goes back to what Ali was discussing, concept shift. And this is probably the hardest type of shift that one can face. Because the relationships are changed, and as I'll explain in a little bit, techniques such as active learning could be quite useful in these cases. And an example of this occurrence is that when you train your data to detect, let's say the task is to detect spam emails, and now you want to use the same model to detect phishing emails. They may have the same features. See, we want, but the tasks are different, and your model, the relationship between these features can be quite different, and your model may not perform as well as you want. Just check the time. All right. If there is any questions, I cannot see them. Just let me know, and I'll answer.
I will
okay. Yeah, just unmute yourself, ask the question, or type in the chat whenever you want. All right. So let's move on and discuss the case for transfer learning where tasks are the same, but the domains are not different. Okay. And there are multiple, as similar to the previous case, there are multiple cases that this would happen. So the first one is that your feature spaces are different, but the tasks are the same. And a good example here is that you have trained your model on grayscale images of trains and bikes and whatever. And now someone presents you colored images of those same objects and same class of objects. So we are not increasing the number of classes here. You have the same number of classes, and the only difference is that the feature spaces are different. One is colored, which is a RGB space, and the other one is grayscale, which has only one dimensional depth in the images. So usually when this happens, when the feature spaces are different, we have to find a mapping between these two spaces. So in this example, it's kind of simple. You can, the mapping is just changing the colored image to grayscale images. And that may change your the performance of your model, and may decrease it. But that mapping you'll probably get a good result by just doing that. And there are other techniques that you can use, such as cropping and padding. Let's say the size of the images are much larger now compared to before, or the dimensions are different. You trained it on rectangular images. Now the images are triangular. Let's say, I don't know, circular, or the X and Y's are different, but the height and the width are different from each other. So you can use cropping techniques, padding techniques to mitigate those issues and map these two feature sets to each other. And there are also more sophisticated techniques for more sophisticated tasks, such as translated. The keyword is translated relearning. If you want to learn more about these techniques, that allows you to create this mapping between these two data sets. One simple way, another simple way would be to train an encoder or another model that actually maps these two data sets together. And that will allow you to reuse your model. So type of, let's say, encoder decoder type of model that takes in excess and spew out the related extau. And you can put that in your pipeline and reuse your model. But there are more sophisticated ways that this is a keyword to look for. Okay, so back to the terminologies that we defined. There are two cases that you may have different domains. One is that your feature sets are different, which we discussed here. And the next one is that your distributions of your features are different, which is covariative, as Ali discussed. So if just the distributions are different, then that means that we are dealing with covariative. For imaging and data, a simple example is we're training on the Google Maps number data set, SVHN data set. Now you want to apply that model for detecting digits, and now you want to apply the model that detects digits on SVHN to MNIST. And imagine that both of them are colored images, RGB images, or you train these on grayscale, so you're not dealing with the first task, but the data look different, but they are the same thing, and the size are the same. Let's say the depth or the number of the color dimensions are the same, but the data looks different, and this is the case of covariative, as we discussed, where you can reuse some of the techniques that Ali discussed to improve the performance of your model here. You can do fine-tuning of the last layers again to have better performance here. And there are more sophisticated techniques in this case, especially for image data, that you can use to mitigate the covariative issue. One of these techniques that I found very interesting is called domain confusion. And the idea is very interesting. So imagine that you have a model, and the model gets some input, let's say images from SVHN dataset, this dataset that we just showed here, and spew out the class label, which is RX 1, 2, 3, 4, 5, 6, 8, 9. And so we have 10 numbers here for class tables, and the inputs are SVHN numbers. So what we can do to fix this issue of having two data sets and have one model which performs well on both of them is that we can have the model, we can mix the data sets in the input and have the model, because you don't want the model to be biased with respect to any of these data, have the model to reduce the loss of this classification loss, and at the same time attach the feature extractor layers of your network to another domain classifier network, which you maximize this loss. So basically you train it in 2 steps. When you go this way, you minimize the classification loss, and in the next step you do you move in this direction and maximize the domain classification loss. So this way your model, so you end up with a model, and you can throw out this part at the end. You don't care about this, but at the end of the day, when you train the model this way, you have a model which cannot distinguish between the two domains, the MNIST dataset, let's say, and the SVHN datasets, these two datasets. So if you give these two images and ask it to classify for you, you cannot do that because you maximize this loss. But at the same time, you minimize the classification label. So the model cannot distinguish these two data sets. It's not biased with respect to any of them. And if you mix these data sets together, you will not be able to distinguish them, but it can tell you the number, which is what you want. And that's the idea behind domain confusion networks, which I find very interesting. The paper is here, you can take a look at it. All right, so that's the first part of the talk, which is about domain classification, domain transfer learning, and different cases of having different feature space or task. And in this part, I'm going to talk about active learning. And active learning is the scenario where let's say you have a model which doesn't perform well, and let's say you're facing a concept shift type of phenomena, or it occurs and your model is not behaving correctly, and you have a very limited resources to deal with this problem, and you want to use your resources as effectively as possible. So you can use active learning to achieve this goal. So imagine a scenario when your training and target data sets are quite different from each other. And let's go to extreme and say there is no overlap between their distributions. And that's the case. If that's the case, you cannot use some of the more passive techniques that Ali discussed, such as sample reweighting to fix the model. So, and let's say you don't know much about the target data set. You don't know its distribution very much. You're not sure about if there's any new features there, any new behaviors that you're not accounting for. And you have a finite resource. You have already spent a lot of money and time on training your model, and you don't want to spend the same. You don't want to start over and train a new model. You want to reuse your model and use your resources as good as possible. So, and let's say they give you a budget of collecting more samples and returning your model. So the goal of active learning is to prioritize the labeling of new data. Such that your model will only be trained on the data that it would have the maximum impact on its performance. Okay, so as we'll discuss later, there are two ways that this would happen. One way is that you want your model to tell you what type of data it needs to perform better. And this would help you to reduce the number of new labels that you have and improve the performance faster than just randomly choosing new label data sets. So this is a scenario of active learning. You have a model which is trained on a limited number of data points. You give access to your model to a limited number of new unlabeled data sets. And you want your model to prioritize the labeling of new data based on some metrics, some uncertainty analysis. And I will talk about these metrics later. So, all right, and the model will then query you, the user, to label the new data, and the model learns on this new labeled data set. So one thing that you have to take note is that this process of sampling may not correctly reflect the test distribution. And the reason is that you are reusing the knowledge of the model on which is trained on your training data set here. So if the distributions are quite different between your training and test data, then this knowledge may not accurately represent the test distribution, but it's better than nothing. There are two types of active learning, which we're going to talk about. Basically, these are the two big classes of active learning, and there are different models in each one, so there is no one model doing this, but you can generally categorize them in these two ways. One is called pool-based active learning. So you give the model a large pool of data, Do you still see my page? There was a notification on my computer.
Yes, I do.
Okay. Okay. I don't know. There was an error. I thought there was an issue. All right. So, so you give your model access to a large pool of unlabeled data points and ask it to prioritize training on them, to rank them. Let's say this is not informative. This part, this is informative. That's not. I don't care about that part of the data set. Just let me train on this portion of data. So you give it access to the whole pool. The next one is a stream-based. So it's not always possible to give you access to give access to have access to a large pool of data. Sometimes the data is just coming in, and you want to label it as it comes in, and that's called the stream-based active learning. So when your model see the new data, it decides whether to use it or not, or just toss it out, wait for the next one, and decide whether to label it or not. So this is the case of stream-based, and pool-based, you already have access to a pool, and you can rank them. In the stream-based, we cannot rank them because we are not seeing all of the data at the same time. Okay, so what are these uncertainty analysis that active learning uses to decide whether there is enough information in your data or not? So these metrics, we're going to go through some of them. We are going to go through some of those uncertainty sampling techniques, but that's not the only technique that is used. As I've listed here, there are cases that you use the first one is the uncertainty sampling. Let's just talk over it. That you select the data that your model is the most uncertain about. There's a method called ranked batch mode sampling. So you sort the samples and you select multiple instances at the same time. Let's say it's kind of like a string-based, but you can select multiple samples instead of just one. And there's also other techniques that use some of the gradients of your loss function. Let's say you use the gradient of your loss function to figure out which data point changes your model more significantly. So you can use that information, that gradient information, to decide whether this data point is important or not. And the next one would be expected error reduction, and which is basically using the same loss function and figure out which data point reduces the loss more significantly. And also there are other techniques such as variance reduction, which selects the data points that maximize the reduction in the variance, and many more. There are tons of research papers introducing new techniques for active learning sampling. We're going to talk about a few of the techniques, such as for uncertainty sampling, which is the most basic ones. Also, there are more advanced active learning techniques. One algorithm is called ANDA algorithm, which also take account the covariance shift of the data when doing active learning. So it combines an active nearest neighbor scoring strategy with nearest neighbor prediction. And this algorithm is powerful under covariance shift, but it's a more advanced topic. I just want to put it here. If you're interested, you can look it up. All right, so let's talk about some of these uncertainty samplings. The first one is simply the classification uncertainty, which means that imagine that no, I don't have an example here. So imagine that you have 3 classes. So the field that is shown here, P1 is the prediction on class 1, P2 is prediction on class 2, and the scholar field that you see here shows a prediction on the uncertainty based on the prediction of the 3rd class. So you can see if that data point you have, let's say 1/3 about 0.33 on all of P1 and P2 and P3, you have maximum uncertainty about that data set. And that's the formula is 1 minus the insight that you want to predict given the most likely the most likely prediction given the insight that is already being predicted. So imagine you have 3 classes, and let's say it's 0.1, 0.2, and 0.7 for one of them, and you have 3 of these type of predictions for the 3 classes. You just subtract 1 minus the most likely one that you have, and that gives you the uncertainty value. The next one is classification entropy, which look at the entropy of your predictions. And if I can see, the field is a bit smoother compared to the previous one. And so entropy represents the amount of information in a data. It's a good measure of it, like how many bits you need to represent the information in that data. So so you can use it to have a measure of uncertainty. If the entropy is higher, that means that data point has a lot of information, and as you can see here, it's maximized near the same point as we would expect, that your model is completely uncertain about all 3 classes. Let's say you give it a new data point and it predicts 1/3, 1/3, 1/3. And I don't know which is exactly equal for all 3 classes. So that data point is very valuable, because if you train your model on that, it will learn about that part of the target data set. So, and that allows you to have a measure of uncertainty of that data point. So one technique is entropy, another one is I think I make this. There was another one which I think I duplicate this slide, and when we post the slides, I'll fix this. But there are various techniques that you can do the same type of, you can tackle the same problem. And these are the most basic ones. Another technique is called query by committee. So imagine you have a lot of models on the same data set, and these models differ based on hyperparameters, seed, or the structure. And you use all of these models to vote on an output label. And you can use the votes of those models as a measure of uncertainty. Let's say you can choose them. You can use the difference between 2 categories with the most votes as a measure of uncertainty. You can use the vote entropy as uncertainty, or combine the entropy with KL regions and other techniques that you can use here to find a measure of uncertainty based on the votes, the ensemble of the models that you have, the votes of the ensemble of the models that you have. So this is also another technique that is used. And many, many more. If you're interested, you can look it up. There are tons of papers on discussing all the various techniques for active learning sampling. One thing that I wanted to mention is that there are certain challenges if you want to combine deep learning with active learning. The first one is that neural networks tend to be overconfident in their output, and that's not good for us, because that wouldn't give you a very accurate uncertainty measure, I would say. Also, they're better trained on a batch of data, but usually active learning scenarios, you're dealing with single data points or a few data points. And to tackle this issue in the literature, Bayesian neural networks are used, and also techniques such as batch mode sampling have been introduced, so you can select a batch of data for active learning instead of just a single data point. And you can look these techniques up, and they're more advanced for this talk. Let me make sure that check the time. Okay, and here are some of the references that I have used here. You can have a look. And yeah, that's it. If there are no questions, we can move on to the hands-on tutorial part. Sadaf, how much time we have? It was up to 6, right? If I'm not mistaken.
Yes, we have still time.
Okay.
So I'm gonna
Okay,
share the Colab link again, because I already shared, but just for those who join later. So here is it. But we have time for a few questions. If not, then we can go into the hands-on. Are there any questions about active learning and transfer learning? You can either write your questions on the chat, or you can unmute yourself and introduce yourself and then ask. That is better for the
Also, yeah, the chat. Let's see.
I received some questions regarding the slides. Are we going to share them?
Yes, we already responded to those in the beginning. Yes, the slide and recordings will be shared later. Okay. I guess there isn't any questions. So Mehdi, please proceed with the collab. Maybe while you're doing the hands-on, there might be some questions.
We have 20 minutes, which is more than enough. All right. So the goal of this hands-on tutorial is to give an example of how you can use a domain classifier to detect and correct covariance shift. And adapt is maybe a better word here. So you want to detect and adapt for covariance shift using sample reweighting that Ali discussed earlier. We are also going to discuss alibi detect library, which is a very comprehensive library for detecting covariance shift and label shift. And we're going to give you one example from the tutorial of alibi detect. And the goal is here to just introduce you so you can check whether you can integrate this library in your pipeline. All right. So let's just first simply import a few libraries. Actually, I think I have ran all of the columns here, so I won't spend time doing that. So we're going to use first the first part of this tutorial is about creating a domain classifier on a shifted data, and first detect covariance shift and then correct for it. Okay, so we're dealing with the first part of the tutorial. So I'm going to use the Boston data set from scikit-learn, and this is a description of the data. So the attribute that we want to predict is the price of houses in Boston, and there are 13 predictive metrics that we can use, like the number of rooms, the age of the property, and etc. And this is a common data set that is used for practices. So we first load the data and put the price as the target that we have. So we get a data frame from our data and use the same columns of the Boston, and then we assign a column to the target of Boston, which is just price. And here we drop, we just separate, we put price in Y and X only, or feature space. And we split the data with 20%, with the test size of 20%. And here we have our training and the test data set. So we create a copy of our test data and we shift it. Okay. So we name it, our goal is to create a fake shift data. So because of this practice, we didn't have access to a shift data set. So here we're just going to shift it ourselves manually and find a way to fix it with our model without having access to this shifted data set. So we make a copy of our test data, and here I'm going to shift the number of rooms of the data. So our goal will be to train a model on the original data set and figure out a way to fix it and apply the same model on a data set of the same type, but with a different distribution of a number of rooms. Let's say you just train it for the prediction in Boston, and you want to use the same model to do the two prediction in Texas. And Texas, the houses are larger, and the average number of rooms are increased, or other metrics can also differ. But for this tutorial, we only focus on the number of rooms. So I'm going to just randomly increase the number of rooms in our the shifted test data. So as you can see here, I'll just randomly choose one of these numbers and apply the shift. And when we do the histogram of the shifted of the number of rooms in our test data and the shifted data, you'll see that the number of rooms are in the shifted data is a bit higher than our original data. And remember, these are both test data that we are not going to use for our training. Now, I do a linear regression simply on our original training data set. Okay, and I look at the performance of our model, the RMS error for the prediction of the price is 4.6, R squared is 0.75. Okay, now I do I test this model again on the test. This is for the training, right? So I do it on the test data set now. The performance drops as we expect usually. Usually it shouldn't, but here it does. It could be either equal or worse on the test data set. Remember, this is not shifted. So error is 4.9, close to our training, and R squared is a bit lower, 0.67. Now we evaluate the performance on the shifted test set, and the performance is horrible. So by just changing the number of rooms, you can see the model that you have trained now performs horribly on this new shifted data set. By just not increasing the number of rooms, simply by 1 or 2 or 3, it's not a big change. It's not like that the number of rooms have increased from 1 or 2 to 100. It's just a little bit higher. But the performance of the model has decreased significantly. And here are just importing the Rock score, which I'm going to use later for the domain classifier. So my goal right now is that I want to first I want to detect the shift, if there is a shift or not, okay? And I'm going to use this Rock score to figure that out. So I mix my training data and the shifted test data set together, and I label the training as is training. So simply is training, if the test shift will be 0, and if it's training, it's going to be 1. Okay. So I label the training data set with 1, and the shifted test data set with 0, and I concatenate these two data together. Remember, these are the feature spaces. And I want a model, I want to train a classifier to see if my classifier can actually distinguish between the training data set that I have and the test data set. Because if they come from the same distribution, your domain classifier should not be able to distinguish between them. It's just like you have separated the same data into 2 sets, and if they're the same, if they're really the same, your domain classifier should not be able to detect it. So let's train a classifier on it. So I use a random forest classifier with a depth of 2. And if I print the ROCOC score, you'll figure out that the ROCOC score is very high, 0.96, and that means that your classifier is performing well and can distinguish between the training data set that you initially train your model on and your shifted test data set. So we know that the data is shifted. Good. So that's our first goal. And we can also gather more information from this model. If we look at the feature importances of this domain classifier, you will see that the model, the classifier, uses number of rooms much more than other metrics to distinguish between these data sets. So we know which feature has shifted just by looking at the feature importance of the classifier, the domain classifier. Okay, so good. So we got 2 information. First, ROCOC score was high. So, or you can use other metrics if you want, that's fine. And that allows us to know that, yes, there is a shift. Second, we look at the feature importance and we know which feature has shifted, which is the number of rooms here, which we already know because we did it ourselves. Okay, now that's the first part of the training. But I want to use, I want to also first give a more visualized 2D example because it has many features, and if I fix it, it's gonna be it's not gonna be as visual as I want. So I'll also do it another time again for another data set. This is just a linear data set, so let me plot it. So this is the training and the test and the real and the ground truth of our data. So forget about the previous data. We have moved on from this. So the goal of the first part was to just detect shift. And now I'm going to use a new data set for the next part, which is better for the for visualization. So here, if you look at this graph, this is the ground truth, the golden standard of the model that we want to reach. So the black one is the ground truth, but we have collected these training data points on it. Okay, but the test data, as you can see, they're all sampled close to 0, so they're kind of biased here. Okay, our sampling technique is biased. So sorry, I shouldn't say sampling. The test environment is not representing the exact test training data that we had. So the training looked at the whole domain, but in reality, our test domain is only focused on this area. Now imagine you want to have a linear model here. So these are also the distributions. You can see it here. So the test data set is close, the distribution is close to 0, but our training is close to 0.7, but there's an overlap between them. So we are going to utilize this overlap to fix this issue. Okay, so imagine I train a model on the training data, the blue dots, and use it on the red data, the test data set. I get a score of 0.54, which is not very good. And if we visualize it, we can see that this is our model that we have trained, and this is the test data point that we want to predict. And you can see this is a good fit, a linear good fit for the blue ones, but it's not a good one for the red one. So we want to figure out how we can fix it. So we train exactly the same way as we did it before with the is training one for domain classifier. So we created a domain classifier. This one I chose logistic regression, but it's fine. You can use any type of domain classifier as you want. So I train a logistic regression to distinguish between my training data set and the test data set as we did it in the previous step. But we want to further use the information from that domain classifier. So if I plot the, I don't have the, maybe if I go back to the slide, you may be able to see it, that we want to use the ratio of the predicted probability on our training, okay, divided by the predicted probability of the other field. We can come up with the betas of our prediction. So basically, let me actually open up the slide. I think I have to stop sharing. It's better to just show it here before moving on. If I go back to Ali's slide on this topic, we find a slide here. So our goal is to find this beta, the weights that we want. So this beta is the predicted probability, the probability of predicting. Here, -1 was, if I remember correctly, was the probability of finding the if the data is part of the test data set over the probability of finding a data is part of the training data set. So, and if I go and visualize this is a better visualization of this, is that it shows that these points related to the training, so it assigns a weight to each training point, that whether that the probability of that training data point be inside or test data. So as you can see here, as we get closer and closer to this location, the sample weight increases. So we have a higher weight close to this region compared to this region. So this is a probability. So it's a beta that value, this weight, is representing so it's higher when your training data point is closer to the real test data set. So, and you want to give it higher weight to the data around here than here. So, and that will allow you to improve the performance of your model. So if I go back to the slides now, you can see that we have to create a new loss function. If I zoom in a bit, if you calculate this beta, we have to now multiply beta with our data with the loss of the with the loss function that we have, which here is let's say MSE different, the mean squared error. And so you have to multiply beta with each of the data points that we have. So we have to design a new loss function. So to do that, I just simply use autograd. This is not the best way to do it, just to be clear. It's a very rough way of finding this error term. But what I'm only doing here is that I'm creating to do the linear test. First, what I do is that I am using these betas. I'm multiplying it with the squared difference of the prediction versus the real value and returning this error. And I use autograd to take the derivative of this and perform the training. And if you do that for the linear function, you'll figure out that this is now the prediction of your training. Remember that we are not using any of a test data set for training. This is the same training data set, but we have assigned more weight to the data points that better represent our test data. And as you can see here, the performance has increased significantly. All right, I have only 1 minute, right? So I'll go to on the next one very fast. So
Mehdi, we have still time, so we have still time. Don't worry about it.
Okay, so should take less than 5 minutes. So that's how we can use a domain classifier to improve the performance of a model and also detect data shift. Next, I'm going to talk about Alibi Detect, which is a library that has implemented many of the detection techniques inside it. And here we're going to use it for detecting label shift and covariate shift. Okay, and this is example. You can find this example inside its tutorial. If it's documentation, if you go to the tutorial, you can find this example. So I'm only reproducing it here, but I wanted to talk about it because it's an important library. So this model simply uses, oh my God, I think I have to install it on my Colab. It's fine. I just use the ones that I've already run. So the goal is to load CIFAR10 dataset that I discussed earlier. It's just a dataset of images of 10 classes, and apply some corruptions to it. So they have different types of corruptions that you can load from this library for practice, if and also testing your model. So changing the brightness, changing the contrast, and etc. So we're going to choose brightness and zoom blur, and apply brightness and zoom blur to some of the images. So they're actually kind of like shifted. So they're going to have a case of covariate shift. Let's say your lens is not clean in some of the images, and that has caused covariation for you. So we have only 10 classes here, and this is the number of classes. As you can see here, the number of items for each class are almost equal. There's an almost equal distribution between them. And if I show you how those shifts look like, this is the original image, and this is the bright. This is increasing the brightness to crop the image, and also zoom blur to blur the image a little bit. And if we train it on the original data set, we find an accuracy of 92%. But if we do it on the brightness, 89 and 60% on the zoom blur. So the shift that we have done had some effect on our prediction capabilities. So they have this KS drift package that uses okay. Let me just make sure that all right, okay. So I'm not sure, Ali, did you talk about this in detail or not in this? I just kind of like, I'm not sure if you skipped over it or not.
I didn't talk about details of KS. I think it is
all right.
beyond the workshop.
Okay.
So maybe you can jump to the results.
All right. So this is KS drift is a technique that uses dual test for our data, and and since our data is multivariate, you may not have only so applying p-test on, you're not applying only p-test on 2 data points. It's a multivariate problem, and uses a technique called Benferroni to correct the test for the KS test for all the data points that you have. Let's say in case of images, that would become testing each pixel with the reference image that you have. So I won't go into details since it's kind of advanced topic and Ali haven't gone through it, but I just want to leave this example here so you can take a look at it yourself. But the idea is that this technique is implemented in this library. So if you don't have a knowledge of it, you can use it. So the way that it works is that it takes an encoder to reduce the dimension of the images, because doing this test, you don't want to do it on every pixel, especially if your image is large. So you use an encoder to reduce the image dimension. You're not training this encoder, remember, it's just simply reducing the dimension of the image. And then you can use this KS drift model inside this library, and given a p-value that you define, you can, which we defined it here for 0.02, I guess, or 5. That will allow you to like 0.05. That will allow you to detect covariance shift. So if we test it on the original data points, we can see there is no drift. But if we do it on the and these are all the p-values of all the features of the encoded images. But if you do it, if you check the drift on the corruption of brightness, it will tell you that there is actually drift happening, and also for the zoom blur. And as you can see, the p-values are quite smaller. You can see that we are applying p-value tests on each single encoded feature. Encoded, I mean the endpoint of the encoder that we have used. And the way that they are combined together is through this Pimperoni technique, but there are also other options that you can choose other than Pimperoni. Pimperoni is the most conservative technique that you can use. So there's also there's another technique, black box shift detection, which is commonly used for label shift detection. This library also has some of the techniques that are used for label shift detection if you want. And feel free to just go through this tutorial and also take a look at the documentation of this library to understand the details of it. We haven't gone through it in the workshop, so I'll just leave this example here for your further research. And yeah, if there's no question, then I think I'm done. Any questions?
Are there any questions? I know it's getting late and then already the end of the day, and then you'll after work and then getting exhausted, but I hope that you get some value and some more information about this topic. Please feel free to unmute yourself and ask your questions if you have any.
Or if they have any question and maybe it's kind of late, please don't be shy. Reach out to me and Mehdi on LinkedIn. We would be more than happy to help you.
Definitely.
Yeah, definitely.
There's one more. There is a question.
Not that I am aware of. There could be new ones. Yeah. So the question is,
you can mention scikit multiflow.
Yeah, you're right. There is one library which is not sure how commonly it's used, but it's called scikit multiflow. Let me check the link and send it to you. Yeah, it's called multiflow. Yeah, true. I sent it in the chat. So this is another library which is used for shift detection. All right, I think.
Yeah, we're all good. So thanks everyone again for joining us today. And once again, you can reach us on LinkedIn, Mehdi, Ali, and myself. And if you have further questions, again, if you are interested in learning more about our report, recent report, dataset shift and potential remedies, you can go on Vector's website and you can find that report, and you can take a look at those 3 different data sets examples that we did in our project and learn more about the details. And thanks again, and have a good rest of the night.
Sedef.
Yes.
There is a question. I'm not sure if it's for me or for Mehdi.
Okay, go ahead.
Adarsh asked, in practice, once we detect shift, we are required to predict the distribution of test. Could you elaborate that one, please? Is it
the distribution of?
We don't need to predict the distribution of test.
No, we don't need to. Yeah. So the goal is that if there are some overlaps between your data set, that the sample reweighting is indirectly predicting the distribution of tests, right? So it's trying to figure out which parts of your test data, training data, better resemble your test data. So it's kind of indirectly predicting the distribution of tests, but yeah, you don't need to know it to do any of these practices. So I hope that answers your question. Sometimes they're quite different, and you may need to have some retraining either through active learning or transit learning.
Perfect. Thank you, everyone. Thank you, team, as well, for a wonderful workshop. And we look forward to hosting you soon.